scientists switch on a strange new form of magnetism in an ultrathin material. Imagine taking a material that normally appears to be non-magnetic, making it only a few atoms thick, and then slightly stretching its atomic structure, and suddenly, its electrons begin behaving as if the material has a completely different kind of magnetism. That is the surprising result reported by scientists studying ultrathin ruthenium dioxide. Researchers say they have found evidence that this material can exhibit a recently proposed form of magnetism called altermagnetism when it is reduced to an ultrathin film and placed under strain. And if scientists can learn how to reliably control this unusual magnetic state, it could eventually become useful for next-generation electronics, spin-based computing, and advanced memory technologies. If you like my videos, subscribe my channel, and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. For discussion, write down your views in comments. So, what exactly did the researchers discover? To understand that, we first need to look at what makes magnetism possible. At the microscopic level, magnetism is closely connected to the behavior of electrons. Electrons possess a quantum property called spin, and the way these spins are arranged inside a material can determine whether that material behaves like a magnet. Scientists have already identified several forms of magnetic order. But altermagnetism is different. It is a relatively new concept in condensed matter physics that combines some characteristics associated with familiar magnetic states while producing a distinct pattern of electron spins. That unusual combination is what makes altermagnetic materials particularly interesting for future electronics. And now, scientists have found evidence that ruthenium dioxide may be capable of entering this state, but only when the material is prepared in a very particular way. A material that behaves differently when it gets extremely thin ruthenium dioxide has been studied by physicists for years. In its ordinary bulk form, researchers have found no convincing evidence that it behaves as a conventional magnetic material. In fact, the scientific community has largely concluded that bulk ruthenium dioxide is non-magnetic. But the new research suggests that changing the material's dimensions can dramatically alter its electronic behavior. The researchers created ruthenium dioxide films only a few atomic layers thick. At this microscopic scale, the material no longer behaves exactly like a large piece of the same substance. And that is where things became interesting. The scientists discovered unusual patterns in the way the electron spins were arranged. These patterns were consistent with the symmetry expected from altermagnetism. The research was led by physicists, including Minchi of Rice University, working with Bharat Jalan of the University of Minnesota and Milan Radovic of the Paul Scherrer Institute. The team's findings were published in Science Advances. How did they detect the hidden magnetic behavior? Well, the researchers weren't simply looking at the material and seeing a magnetic field. Instead, they had to investigate the behavior of the electrons themselves. One of the most important clues is called spin texture. Think of spin texture as a map showing how electron spins are arranged throughout a material. If those microscopic spins follow particular patterns, scientists can use those patterns to determine what kind of magnetic state may be present. To investigate the ultrathin ruthenium dioxide, the researchers used a highly specialized technique known as spin-resolved angle-resolved photoemission spectroscopy, or spin-resolved RBs. This technique allows researchers to examine how electrons emerge from a material and determine important information about their energy, momentum, and spin. The measurements revealed spin patterns that were consistent with unconventional magnetic behavior. The researchers then compared the experimental results with theoretical calculations. Together, the evidence suggested that the ultrathin ruthenium dioxide was exhibiting properties compatible with altermagnetism under the experimental conditions. But there was another crucial ingredient. The material had to be strained. Stretch the atomic structure, and the magnetism appears. The researchers discovered that the unusual electronic behavior depended strongly on the structure of the material. When the ultrathin ruthenium dioxide experienced lattice strain, meaning its atomic arrangement was slightly distorted or placed under stress, the electronic structure changed. And those changes were associated with the spin behavior consistent with altermagnetism. Without the necessary strain, the same material did not show the same evidence. This is particularly exciting because it suggests that strain could become a kind of control knob for magnetism. Instead of permanently changing a material's chemical composition, scientists might be able to manipulate its magnetic properties by controlling the arrangement and spacing of its atoms. That could open an entirely different approach to designing electronic materials. Why does altermagnetism matter? The reason researchers are so interested in altermagnetism is that it could potentially provide useful properties for spintronics. Traditional electronics primarily use the electrical charge of electrons to represent and process information. Spintronics takes advantage of another property, electron spin. By controlling electron spin, scientists hope to develop technologies that can store and process information with potentially greater efficiency and new functionality. This could eventually contribute to smaller and more advanced memory devices, as well as other forms of quantum and spin-based electronics. But altermagnetism is especially interesting because it may offer characteristics that are difficult to obtain from conventional magnetic materials. The ability to manipulate an altermagnetic state using something as fundamental as atomic strain could therefore give engineers another tool for designing future devices. Of course, that doesn't mean a new type of computer memory is about to appear. The researchers are still studying the fundamental physics, but discovering a controllable pathway toward an unusual magnetic state is an important step. Ruthenium dioxide has already been a scientific mystery. There is another reason this discovery is particularly interesting. Ruthenium dioxide has been at the center of a long-running scientific debate. Researchers have spent years trying to determine whether the material is magnetic in its ordinary bulk form. Eventually, evidence accumulated that bulk ruthenium dioxide does not exhibit conventional magnetism. The new research doesn't necessarily overturn that conclusion. Instead, it suggests something more subtle. The same material can behave very differently when its thickness and atomic structure are changed. A large piece of ruthenium dioxide and a film only a few atomic layers thick may therefore have fundamentally different electronic properties, and that is a recurring theme in modern materials science. When materials become extremely small, sometimes only a few atoms thick, the rules governing their behavior can change in surprising ways. The bigger lesson: size can become a control mechanism. For decades, scientists have focused on discovering new materials with useful properties. But increasingly, researchers are learning that they don't always need an entirely new substance. Sometimes, they can take an existing material and manipulate its thickness, atomic arrangement, strain, or environment until a new property emerges. That appears to be what is happening here. The researchers effectively found a way to push ruthenium dioxide into a different electronic regime. And because the effect depends on strain, there is the possibility that future experiments could investigate whether the magnetic state can be deliberately switched, tuned, or controlled. That is where the potential technological importance becomes much greater. But there is still a lot to prove. It is important to emphasize that this is not yet a finished technology. The researchers found experimental evidence consistent with altermagnetic behavior under specific conditions. They still need to understand exactly how the state forms, how reliably it can be controlled, how stable it remains, and whether it can be integrated into practical electronic devices. Those questions will determine whether this discovery remains an intriguing piece of quantum materials research or eventually becomes part of real-world technology. But the result already demonstrates something remarkable. A material that appears non-magnetic in its ordinary form may reveal a completely different kind of electronic behavior when it becomes only a few atoms thick and its atomic structure is carefully strained. And that means the future of electronics may not depend only on discovering new materials. It may depend on learning how to unlock hidden properties inside materials we already have. So, The big question now is, how many other materials are hiding unexpected physical properties that scientists simply haven't learned how to switch on yet? The answer could determine what the next generation of memory, computing, and quantum technologies looks like.